Okay, in the last couple of videos we've talked about the electric field and the electric potential. And when we did that, we sort of talked a little bit about the mathematical formula that described them. So here's the electric field for a point charge, and here's the electric potential for a point charge. They look very similar to each other, and it turns out that they're actually deeply related. And one way to think about how they're related to each other is to be able to look at that representation that we brought up earlier with the energy landscape. So if we draw a picture for a positive charge, and we draw the electric potential graph sort of on top of that to represent this sort of hill structure. We already talked about the fact that the electric field near this positive charge is very large, and as you go farther away, it drops off. So if I'm close to the charge, I might have an electric field vector that looks like this, right? This is not in space, so I'm not drawing it sort of if you will, in 3D space. I'm actually just kind of drawing it along the line here. So this electric field vector actually lives along this axis here. Let's put it that way. If I go a little farther away, which would mean sort of going out here, that electric field vector is going to be a little bit smaller. If I go farther still, it's going to be even smaller. Right? So that was what we talked about in terms of thinking about the electric field for a point charge. Just getting farther away from it, you get a smaller electric field. Now, if you look at this, the size of the electric field seems to map pretty closely to the slope of this potential. It's very steep here, it's less steep here, and it's even less steep here. It's vanishing here, which is not the best drawing, but it is what it is. But the point is that this electric field is actually directly related to the slope of this potential. And that's exactly how they're related. The electric field can be written as minus the 3D slope of the potential function. This is the so-called gradient. Right? Mathematically, if we were to write this out in full-blown gory detail, it would be minus dv dx minus dv dy minus dv dz. Now we're not really going to work with that in 3 dimensions, but so what we'll do is we'll say, let's just take the x component of the electric field. Let's just think about it in 1D, right? So that x component of the electric field is the negative partial derivative of the potential with respect to x. So this is the kind of thing that you would end up working with. Now, this both characterizes the slope piece right here, but it also has this minus sign, and that's important. Because what happens is the electric field actually points along the direction from high potential to low potential. So the gradient, that operator, that slope, tells you about sort of going from low to high. That minus sign is needed to actually tell you that the electric field points from high potential to low potential. Now, the other thing that's interesting about this is this also gives you a description of how you might think about getting the potential from the electric field, right? So what we've done here is figure out, given the potential, what the electric field is. If we were to integrate this, we would be able to recover what the potential looks like. So the description of the potential difference between 2 points is going to be minus an integral of the electric field along some path. In 1D, which is mainly what we're going to be doing it in, we can actually just describe this in sort of the x direction, where this is actually going to be, in 1 dimension, just the integral from some initial x location to some final x location of the x component of the electric field dx. That would tell us the potential between 2 points on the x-axis. So if we actually went sort of along this axis here, we could figure out what the potential difference is between 2 points by taking the integral of the electric field. So what this video is meant to describe for you is how these two equations are sort of intimately related to each other. That is, you can use the idea of the gradient or the derivative to get the electric field from the potential, and you can use the idea of an integral to get the potential from the electric field.